Let's take a look at applying some rules for differentiation so that we no longer have to use the limit definition of the derivative. So let's start with the constant rule. So let C be a constant. If f of x is equal to a constant, then f prime of x is equal to 0. So we have a few examples here. So this notation means derivative of -3. Well, -3 is a constant, and therefore its derivative is 0. Next we have pi. Now it's tempting to think of pi as a variable because we're using a symbol to represent it. But keep in mind that pi is a constant. It is the ratio of circumference to the diameter of every circle. So it is constant, therefore its derivative will be 0. Next, let's take a look at finding the derivative with respect to x of e. E is a number. It is approximately 2.718 and so forth. But it is a fixed number, it is a constant, and therefore its derivative is 0. The next rule we want to look at is the power rule. Let n be any non-zero rational number. If f of x equals x to the n, then f prime of x equals n times x to the n minus 1. So let's go ahead and take a look at these examples of how this might work. So in our first example here, we're finding the derivative, or d dx, derivative with respect to x of x to the 5th power. So in this instance, 5 is our non-zero rational number. And so we have x to the 5th, then f prime of x is going to be 5x to the 5 minus 1. So it would look something like this. 5 times x to the 5 minus 1 power, or we could simplify that a little bit and call that 5x to the 4th. In our next example, we see a cube root. And you may question whether we can think of this as an instance of being able to apply the power rule because it's written in radical form. So what we're going to do is we're going to take advantage of our knowledge of exponents and the relationship they have with radicals. So recall from algebra that the mth root of a to the n power can be written as a to the n over m. And when we can write it that way, then this exponent is now a rational number and the power rule can apply. So what we'll do is we'll rewrite our function here as the derivative with respect to x, or d over dx, of x to the what power? Well, implied within this is that the exponent for the x is 1, and the root is 3, so this would be 1/3. So x to the 1/3 power. Now applying our power rule, then, that is our exponent, so 1/3 x to the 1/3 minus 1 power. So that is 1/3 x to the 1/3 minus 1 is actually -2/3. And then we could continue to simplify that a little bit and write this as 1 over 3 times x to the 2/3 power. And that's probably sufficient. You could additionally write it as 1 over 3 times the cube root of x squared, either one of those would be sufficient. In our next example, we've got 1 over x squared. And again, this may not appear to be a form that the power rule will apply to. However, we can use our knowledge of negative exponents to rewrite this as the derivative with respect to x, or d dx, of x to the negative 2 power. Now, negative 2 is in fact a rational number, and so the power rule can apply. So our derivative here would be negative 2 times x to the negative 2 minus 1 power. So negative 2 times x to the negative 3 power, or negative 2 over x cubed. The next rule we want to take a look at is known as the constant multiple rule. It states that the derivative of a constant k multiplied by a function f of x is the same as the constant multiplied by the derivative. So you can see here that we have the derivative of k times f of x is equal to k times the derivative of f of x. So let's look at a couple of examples. First, we have d dx, or the derivative of 3x squared. So using the constant multiple rule, we can think of this as 3 times the derivative of x squared. And now x squared, we can use the power rule to find the derivative. So this would be 3 times 2 times x to the 2 minus 1. 2 minus 1 being 1, so 3 times 2x to the first power, or simply 6x. Let's take a look at our second example here. We have the d dx, or derivative with respect to x, of x cubed over 1/2. And it may be not clear that this is actually an instance of the constant multiple rule. So let's make that a little bit clearer. We can think of this as the derivative with respect to x, or d dx, of 1/2 times x cubed, using properties of multiplication by rational numbers. Then we can see that we do have this constant of 1/2, so this would be 1/2 times the derivative with respect to x, or d dx, of x cubed, which we can then take our derivative using the power rule there. So 1/2 times 3x to the 3 minus 1, or 1/2 times 3 times x squared, which we can then rewrite as 3x squared over 2 through properties of multiplication of rational numbers. Our third example here, again, doesn't necessarily look like an opportunity for the constant multiple rule. However, much as we did before, we can rewrite this as the derivative of negative 3 times 1 over square root of x. Then we can use the constant multiple rule, so negative 3 times the derivative of 1 over square root of x. And at this point, we need to think about using the power rule. We need to rewrite our function 1 over square root of x. So let's go ahead and do that. So we would have negative 3 times the derivative of 1 over x to the 1/2 power. And then now that x to the 1/2 power is in my denominator, so we bring it up to the numerator by rewriting that as x to the negative 1/2 power. At this point, we can use the power rule to find that derivative. So we would end up with negative 3 times negative 1/2 x to the negative 1/2 minus 1 power. Or, let's see, negative 3 times negative 1/2, that gives me a positive 3/2. And then x to the negative 1/2 minus 1 is x to the negative 3/2 power, which I can then rewrite using the ideas of negative exponents as 3 over 2 times x to the 3/2 power. I hope this helps.